The topic today is hydrogen hazards and gas detection. So we're looking specifically at gas detection, but we're looking at it through the lens of hydrogen, and specifically we're looking at an electrolyzer case study. So hydrogen is getting a lot of mind share, a lot of attention now. There is a very large amount of capital being deployed into hydrogen and hydrogen projects. There's a lot of research in this area, and I figured it would be a good time to present some information. We're going to be presenting a lot more of this information because Conexus has been working with a lot of the key manufacturers that are building these systems. So we've been engineering these systems and the safeguards around them since before they were even being commercially deployed. In terms of where did this come from, I gave this presentation originally during the Global Congress on Process Safety earlier this year. I highly recommend the Global Congress on Process Safety. Next year, it's going to be in New Orleans, which just makes it even 10 times better than it normally is. It's a great format for learning a lot of information really quickly, but the downside is that you've got 20 minutes to give your presentation and 5 minutes to answer questions, which is why we will always follow up our GCPS presentations with a full webinar where we can answer questions on the fly, go at our own pace, do a deeper dive, and delve into the issues in a lot more detail. Okay, so hydrogen. What is all the hubbub? Why is there such a big discussion and interest all of a sudden in hydrogen where, we've had hydrogen for a long time. We've known how to make hydrogen for a long time. We've had fuel cells for a long time. But recently, there has been a big push by society into green energy, or a little bit more specifically, decarbonization. And the trend toward decarbonization wants us to move toward energy sources that don't generate atmospheric carbon dioxide, basically. So a lot of the interest is in electricity, and we can generate electricity through windmills. We can generate electricity through solar panels, but right now there's an issue of storage and transport because we also have this competing factor that says, well, these giant battery systems that we're starting to deploy, they are not as environmentally friendly as we would hope in terms of the mining that needs to be done. And they're actually also a bit of a safety issue. I've had other presentations that I've given related to the hazards of lithium-ion batteries in terms of their self-accelerating decompositions. Lithium-ion battery fires aren't fires. They're self-accelerating decompositions, which is a completely different animal. Now, they also have a component of a fire that results from the products of the decomposition, but that's not the topic of today. If you're interested in the safety hazards of lithium-ion batteries, go into the Conexus website, look at our inventory of previously given webinars. There's a great webinar on the hazards of lithium-ion batteries. So in terms of getting the energy from where we can create it to where we're going to consume it, a lot of engineers, a lot of people are looking at hydrogen to be that mechanism that's going to allow us to store energy, that's going to allow us to transport energy, so we don't limit society to when the wind is blowing or when the sun is shining. Now, green hydrogen, there are a lot of different ways to create hydrogen. The most common one right now is through steam reforming of natural gas. But we can create green hydrogen through hydrolysis of water, and I'll kind of explain a wide variety of different methods that can be used to generate hydrogen from different energy sources that have different strengths and limitations. And When we have hydrogen, we've got flexibility. So you can have hybrid transportation vehicles that have smaller batteries that are safer and cause less environmental damage in their generation, but you're able to use hydrogen through a hydrogen fuel cell to convert that hydrogen into electricity. But hydrogen is flexible because you can use hydrogen in internal combustion engines, and you can use it in turbines to generate electricity also. So very flexible fuel, but it does have its hazards. So hydrogen, as we know, is a gas at ambient temperature and pressure. It is a very, very, very small molecule, which generates a lot of hazards in transportation and storage. But just looking at the traditional process safety hazard, flammability and explosivity are very high. So first off, hydrogen has a very wide flammable range. So if you look at the natural gas that would be coming into your home, if you have natural gas heaters, water heaters, what have you, it's going to be flammable in the range of about 5% to about 15%. That's your LFL and your UFL. Hydrogen, on the other hand, is flammable as low as 4% and all the way up to 75%. So that flammable envelope is gigantic for hydrogen in comparison with other fuels, making it easier to ignite and having a larger range, shall we say, of conditions where flammability is possible. Okay, so we know that there's a wider flammable range, a lot more situations where it's flammable, but it's also a lot more easily ignited. So very low energy sparks, very low energy sources of ignition are able to ignite hydrogen where they would not be able to ignite a natural gas or propane cloud. So for natural gas, we're looking at about 2.29 millijoules to ignite natural gas, but only 0.02 in terms of millijoules to ignite hydrogens. The conditions where it's flammable are much broader, and you can ignite it a lot more easily, which actually has ramifications in the cost and type of design that you're using, because while you might be in a class 1 div 2 area, meaning that you have intermittent possibility of a flammable gas, you're in a different group because you need to even more severely restrict the amount of energy in a device to be able to make it intrinsically safe. Now, hydrogen gas clouds can also be explosive. They're flammable, but they're also explosive. One of the federal agencies that I think is totally worthwhile is going to be the Chemical Safety Board. What you're looking at is AB specialty silicones, or what used to be AB specialty silicones. So go to the CSB website, csb.gov, and download a copy of the CSB report about this incident. Now, the accident that we're looking at here has absolutely nothing to do with green energy, energy transition, or any of that. The hydrogen that they made here, they made by accident. It was not on purpose. Basically, in their production, they're kind of doing small batch production of specialty silicone products, and they inadvertently mixed the wrong chemicals together. And when they did so, they liberated a bunch of hydrogen into the building. And there's a key that we're going to get to a little bit later on. And some of you might have seen the web post that I posted late last week. In terms of hydrogen, one of the greatest factors contributing to the risk is, do you have it inside? Because if your process that can generate hydrogen is inside, your risk is dramatically increased, because now we have something that can trap that hydrogen and create a flammable cloud. And that's what you see here. So in this event, they inadvertently mixed chemicals together that they shouldn't have. The building filled with hydrogen. found a source of ignition and basically destroyed the building. So this is the building you see is decimated. There were, I think it was multiple fatalities, a handful, 2 or 3. I don't remember off the top of my head, but definitely go to the CSB website to get more information on this. The key point of what we're talking about here is if you have an electrolyzer and you have it inside a building and it leaks hydrogen, what you're looking at, can be the result. And that's what we're trying to avoid. Okay, now I mentioned that there are a lot of different ways to create hydrogen, and not all of them are, shall we say, part of our decarbonization effort. Not all of them are green. When most people say, I want green hydrogen, what they're actually talking about is I want to generate my electricity from a renewable method, like solar panels or wind. And then I want to take that electricity, put it into my electrolyzer, and generate hydrogen with it. So that's going to be the one over here, the green. But there are different ways to do it. So the most common one is going to be the gray method over here on the left, where we're going to use fossil fuels, most commonly natural gas, and we're going to use steam forming, pyrolysis, some sort of partial oxidation to generate the hydrogen. Well, what happens when you peel the hydrogen molecules off of a methane molecule? You're going to be left with a carbon that's going to be a CO2. So we're basically trying to use electricity to obviate the need for something that's going to put CO2 into the air, but that process of creating that hydrogen put CO2 in the air, which is why you're seeing right now in the short term a lot of this guy in the middle, which is the blue hydrogen. So with blue hydrogen, we're going to use our typical processes, steam reforming of natural gas, but we're going to catch the CO2. So the CO2 that we put into the heating of the steam reformer and the CO2 that we generate by stripping the hydrogen molecules off of the carbon in the methane, we're going to capture all that CO2, purify it, not because it needs to be pure, but because we just want to capture the CO2. And then we're going to sequestrate, is that a word? Sequester the CO2. So take that CO2, compress it, put it underground in some sort of cavity, usually kind of, replacing the volume of oil or natural gas that gets pumped out of old reserves. So this is very common. As a matter of fact, I'll just kind of let you in on Conexus is working on one of these projects right now, where it's happening in Donaldsonville, Louisiana, where they're building a new hydrogen plant. And we're separating out the CO2, sending that on to another company that is going to go sequester it. As a matter of fact, now it's a little bit off topic for what we're talking about here, but they're actually then going to take that hydrogen, convert it to ammonia, and then move the ammonia around. So that's a topic for another day, in that it's even easier to ship and transport ammonia. You're going to get a higher energy density in ammonia than in liquid hydrogen, which requires cryogenic temperatures, and it's extremely difficult to ship around. So ammonia as the method for moving hydrogen around is a topic for another day, but I assure you it's an interesting topic. Now, there are other colors. We've got our brown and black hydrogen, where we're basically stripping the few hydrogen atoms that are sitting on coal off to create hydrogen. So that one probably pound for pound is going to generate way more CO2 during its production than the gray. The yellow here is kind of, wanting to clarify, well, not just renewable. It's not enough to be renewable. I want it to be from solar power. Now, this last one, I've been kind of on this slide for a long time, but this is a little bit more interesting for the more practical, less pie in the sky engineers, as opposed to kind of a little bit more dreamers, if you will. A lot of engineers like myself are kind of concerned about the energy transition in terms of we're pushing a lot of consumption of electricity without really thinking very hard about where that electricity is going to come from. And, there's the idea that, well, just more windmills and more solar, but windmills and solar are not without their downsides. And realistically, I don't think it's possible to put up enough we don't have enough area to put up enough solar panels to meet our energy needs. So this is my opinion. If we keep pushing through in electrifying everything, there's no way we're going to get out of this without going to nuclear. But that's just my opinion. You can toss arrows at me all you want. Now, nuclear is seeing a renaissance now because there is a lot of new technology that is making nuclear dramatically safer. And specifically the use of new pebble bed reactors. We at Conexus have been doing a lot of work with companies like TriSoX that are developing the new nuclear fuels, where instead of kind of a rod or a core of uranium, you're taking a microscopic speck of uranium and putting it in kind of a ceramic ball that can withstand the highest temperatures that will be generated in that nuclear reactor, basically making it inherently safe against thermal runaways. So I don't know if there's anyone from Dow that is in the chat right now in the presentation, but I read that Dow is actually going to install one of these new TriSoX pebble bed reactors in their Freeport facility. That was reported in the news. I haven't talked to anyone from Dow about it, but they're going to use that to do a lot of the powering of their Freeport chemical complex. So anyway, any method that you can use to generate electricity can be used to generate hydrogen from that electricity. And kind of this is another reason why I see hydrogen being so valuable, because it's flexibility. We can generate electricity in a multitude of different ways. We can directly generate hydrogen even using non-electrolysis methods. So in terms of transitioning from point A to point B, we've got a lot of flexibility using hydrogen as that route that we don't have if we just kind of limited ourselves to bigger and bigger and bigger and bigger and bigger batteries. And even on batteries. All right, so if we're going to make our hydrogen from electrolysis, how are we going to do that? There are a number of different methodologies. Kind of the oldest way is going to be the alkaline electrolysis cell. And basically with an electrolysis cell, we're applying an electrical potential across the fluid, and that's causing our atoms to separate. So you'll start with a water and you're going to separate it into hydrogen and oxygen. Now, in the old school electrolysis cells, they were originally actually created to make chlorine. So we're putting in a brine, a salt water into our electrolysis cell, and we were trying to make chlorine. So that's kind of a little bit more of the genesis of the electrolysis. But that same methodology can be used to create hydrogen and oxygen if you're using water instead of brine. The current top dog is the polymer electrolyte membrane. So most of the hydrogen that you're seeing created today is being done with a PEM. polymer electrolyte membrane. And there is a lot of large scale commercial production of PEM stacks. So PEM stacks are a known quantity. There are major manufacturers that are cranking these things out as fast as they can in very large scale. So that's kind of like the proven methodology today. Going forward, we're constantly doing research, and there is a technology called solid oxide electrolysis, which happens at kind of higher temperatures, and we're looking at much better efficiencies than the polymer electrolyte membrane. So that's kind of one to watch out for in the future. It's not quite ready for prime time, whereas the PEM is the it girl, shall we say, for right now. So what do these things look like? All right, so I love this picture because it gives you some context, because we have a human being here and we can compare that to the size of the PEM stack. So what you're looking at here from another one of our customers, this is from Plug Power. Plug Power is one of the big players in creating PEM stacks. This is one stack. So when you look at the stack, there's going to be multiple layers. You could see the different layers in the stack, and they're all basically layers of this. So we're going to have water coming in, and then out the top, we've got a pathway for our hydrogen. We've got our pathway for an oxygen. Now, the PEM stacks are generally going to be about this size, regardless of the volume that you're creating. So instead of creating bigger and bigger and bigger and bigger and bigger stacks, we're going to put more and more of them in series and in parallels. And in talking with another one of our customers, not only are they stacking these in the X direction and the Y direction, they're also stacking them in the Z direction. So three-dimensional matrices of PEM stacks is what we're looking at to try to get the volume of hydrogen that's going to make this commercially successful. Now, you generally don't just buy the PEM stack. These companies that are supplying electrolyzers are generally going to kit it for you. And again, shouts out to my customers. Plug Power is one that you're going to see here. You're going to see an example of an electrolyzer system. And then another one is Cummins. Cummins is another big supplier. So when you look at this, you're going to get an entire kit instead of just the electrolyzer itself. So if you look at this picture, so just kind of think about this stack on top here. When I go to the other picture, you'll see that that is sitting right there. So in this case, there is 1, 2, 3, 4, 5 per side, a total of 10 electrolyzer stacks in parallel generating hydrogen for this facility. And the equipment that's included in here is the water handling before you go into the PEM stack, which is going to include filtration, ion exchange, finishing with carbon filters, the PEM stack, and then the processing of the product. So we're going to get our hydrogen, we're going to dry it and compress it, we're going to get our oxygen, and depending on what your needs are, you might release it back out to the atmosphere, or you might dry it, compress it, and sell it as a product also. What's also interesting is that there's a lot of different varieties and a lot of different hazards. So the electrolyzer kit here is designed to go outside. There is a lot less risk here, but there's also higher maintenance requirements and higher unavailability, shall we say, because it is outside. It's exposed to the elements, it's exposed to rain and sleet and windstorms and sun. So you're going to get more failures, but when a failure occurs, generally your hydrogen is going to waft out harmlessly. Whereas, and again, I don't want to say that one manufacturer is doing it one way, the other manufacturer is doing it the other way. They're not. All of them, and there are dozens at this point in time, I'm just showing you a couple of the big dogs, are going to package things different ways. So this is an outdoor arrangement on the bottom that you'll see from many manufacturers, but you'll also see the top format is extremely common due to shipping. So if you look at the box here, you'll see that this electrolyzer was built in a standard shipping container. So all of the equipment, including the electrolyzers, the compression, the water treatment and filtration, is all stacked inside this container. That's great for shipping. It's great for protecting the internal equipment. But if hydrogen leaks into this container, it's trapped. You've got a trapped gas cloud. If it finds a source of ignition, now you're looking at potential serious vapor cloud explosion issues. So this is kind of how the PEMs are going to be packaged and going out. Now that we've kind of gone a long time in explaining what it is we're looking at the risk of, let's take a look at some of the risk analysis. So here in my favorite PHA tool, Connexus Open PHA, we looked at a deviation for an electrolyzer. And just kind of a word for those of you, if you're thinking about coming to the Global Congress on Process Safety next year, I've submitted a paper to do a template to kind of explain a template HAZOP of an electrolyzer. So that's going to be coming up GCPS this spring. It's based on work that I'm doing right now with Purdue. Purdue has a process safety center that does a lot of safety research. And one of the grad students that I am personally working with right now is looking at creating a template risk assessment of an electrolyzer. There's a lot of hazards. Oddly enough, one of the weird things that I learned in my research is that for electrolyzers, there are more accidents related to the oxygen side than to the hydrogen side. That's kind of unexpected, but if you have leaks in if you have leaks in the oxygen, small leaks in the oxygen, and the workers are exposed to and around that all day long, the high concentration oxygen is going to permeate and saturate their clothes. And as soon as they leave the building, leave the controlled area, if they find a minor source of ignition, their oxygen saturated clothing will catch on fire and burn violently. So that's kind of some scary new stuff. Anyway, getting a little bit off topic, but good information there. Let's look at the hydrogen side.
Hey Ed, real quick, we got a question in the chat here.
Sure.
On your last slide, I think someone's asking what specific model or brand is that unit?
This one is a Cummins Hylizer. And this one is from Plug Power. I don't know the make and model off the top of my head.
Okay, thank you.
Mm-hmm. Okay, all right, so deviation, leak. So I've got a leak of hydrogen, and you could get leaks of hydrogen in multiple different places. Failed gaskets, failed fittings, improperly tightened fittings, fittings that have come loose. There are a number of different ways you could get small leaks of hydrogen. Now, the consequence to this can be dramatic or it can be negligible. And this is where I will refer people to the web post that I posted on the Connexus website late last week that basically runs through some rules of thumb. What you're looking at is for indoors. So there are times that you want to be able to detect hydrogen leaks. Number one is if you are indoors, because if you're indoors, your hydrogen is going to shoot to the ceiling, it's going to spread out, and it's going to kind of start to sink down. You're going to get an accumulation of hydrogen, searching for a source of ignition to cause a massive explosion. So if you're diddling around with hydrogen inside a building that doesn't have proper ventilation, you're going to want to have gas detection, and you're going to want to be able to take some sort of action on that gas detection, which is another source of bad news that I'll get to in just a second. Okay. Now, if you've got this guy and you're outside, small leaks of hydrogen, I'm not going to recommend that you try to detect those leaks with a gas detector. The gas is going to go straight up. There's no humans, there's no sources of ignition above where the release occurs. It's not a problem. Don't worry about it. But if your hydrogen, even in an outdoor application, leaks and it goes up and there's like another deck possibly occupied by people that are, of course, wearing a hard hat and safety glasses, then even in an outdoor application, you're going to want to detect if there's something above where the release occurs. So
Another question,
indoors
Ed.
and outdoors, when there's something above you, are the situations where you're going to want to consider gas detection. But if you're outdoors, there's nothing above you, it's probably not worth the effort to try to detect gas releases.
Another question, Ed.
Sure.
Can you explain why H2 would sink indoors?
It's not really sinking. Of course, all of this assumes that it's not cryogenic. If we have a hydrogen as a cryogenic liquid, it is weird stuff because you will have a very low temperature, dense gas cloud. It will move and behave like a dense gas for a long period of time before it warms up. But let me try to, I'm going to do a drawing right here. And when I get to the 2 slides from now, this will make a lot more sense. But if I have a building and I have a leak source, what's going to happen is the hydrogen is going to travel straight up, but when it hits, it's going to pancake out and spread along the roof. If the leak is allowed to continue and continue and continue, and we're kind of assuming that we're overwhelming the HVAC system's ability to get rid of it, then this cloud is going to get deeper. But because it's sitting on the roof, when I say deeper, the pool is actually kind of moving down. Does that answer the question?
Yes, it does. Thank you.
Okay, yeah. So yeah, I'm not saying that it's sinking. I'm just saying that you've got kind of an inverted pool that's getting deeper and deeper. All right, so if you're indoors and the electrolyzers that we're looking at for this particular case study were indoors, got a potential for hydrogen accumulation at the ceiling in the flammable range. If we have a source of ignition, we can have an explosion. The explosion can cause a potential collapse of the facility, and it could result in multiple fatalities, as proven out in that CSB report for AB specialty silicones. So we'll give that a safety category. We will say that the severity is very high, and then we will look at our safeguard. So right now I'm just looking at a HAZOP worksheet, not a LOPA worksheet, but some of the common safeguards are going to include a ventilation system. So I've got an HVAC system usually that is pulling air. We're putting air in and pulling air out. So that's directionally helping us, but depending on the size of the relief, it might not be enough. Some buildings that know that this is a problem aren't built with a flat roof, and that roof has a ridge vent, which basically will allow your gases to migrate out. So again, these are all possibilities, but as engineers, we need to look at our design basis leaks and make sure that they're going to appropriately do their job. That wasn't the case for the facility that we're looking at. Another safeguard, we've got electrical area classification, but remember how small the energy requirement is to actually light off hydrogen. And then finally, another common safeguard is I'm going to use some sort of gas detection system that has an automatic shutoff of the PEM electrolyzers. Now, I'm telling you that this is a very valuable tool. I'm going to tell you you want to do it. I'm going to tell you to design it. But one of the scary things that I have learned in my recent research is electrolyzers don't shut off fast. So you're talking about a lot of energy, And the typical electrolyzer has a huge degree of capacitance. So even if you detect hydrogen and you stop the electrolyzer, you pull the contactors and you stop feeding it with more electricity, it's still some period of time, many seconds, possibly even many minutes, that it's going to continue to generate electricity before you burn off the entire capacitance. So that's something, keep that into the back of your mind when you start looking at process safety time issues, because just because you de-energize the electrolyzer does not mean you stop making hydrogen. Okay, so in this case, we had our PHA recommendation of implementing a gas detection system that is going to detect releases and it's going to shut down the electrolyzer. Which brings us to, how do we design gas detection systems? Well, we are going to follow the ISA 84.00.07 technical report. And that technical report tells you you need to do a risk analysis to determine what your what your targets need to be. And for a gas detection system, unlike a safety instrumented systems, it's more than just the probability of failure. As a matter of fact, the probability of failure of the electronics is an almost imperceptible, vanishingly small component of the probability that a gas detection system won't work. The great preponderance of Conexus's customers don't even worry about the PFD of the fire and gas system because it's this guy that's always the problem. So what is that guy? Gas detection systems don't work if the electronics don't work. That's the PFD average. But they also don't work if a detector is not located in the gas cloud. So I need to make sure that I have the appropriate number of detectors and those detectors are in the appropriate location to be able to detect my releases to a sufficient degree of coverage. So coverage is the term that's defined in this technical report. It is the most important, it is the key metric for gas detection and fire detection systems. What the coverage is, and I'm talking about scenario coverage, which is definitely what you want to do for gas systems. It is the fraction of releases that are detected, given the fact that my piece of equipment can leak in multiple different directions. It could go north, it could go south, it could go east, west, it could go up, it could go down. If you're outside, the wind can be blowing in all kinds of different directions. So all of that needs to be considered when we pick a target for how good the coverage needs to be and confirm that you achieve that coverage. The last item is called mitigation effectiveness, which is I detected that a gas cloud exists and I took an action, but the action did not result in safety. So specifically for this item, your mitigation effectiveness is going to be a function of time. Let me step back and give you another example. So if I have a fire detection system on a compressor and I have cans of Novec to where when I detect the fire, I'm going to release the chemical suppressant. I've designed the chemical suppressant to be able to put the fire out. But there's a certain probability that somebody might have left the fire doors open. And when I release all my Novec, the Novec wafts away and it doesn't put the fire out because somebody forgot to close the doors. So that's an example of an ineffective mitigation. I detected the hazard, I took action, but it didn't result in my consequence not occurring. So here, for mitigation of effectiveness, we're really looking at time, and that's very common. So the faster you can detect the release, the less likely it is to result in a consequence because you're decreasing the amount of time available for your gas cloud to find a source of ignition. And again, in terms of this mitigation effectiveness, you need to remember when you de-energize that electrolyzer, it's still going to keep making hydrogen for some period of time. So instead of the one factor of SIL for a safety system, for a fire and gas detection system, I have 3 factors that I need to consider. Now, there is a process for doing this. I mean, you could go full-on quantitative risk analysis with event trees, more power to you, but also ISA 8407 has a semi-quantitative approach that's going to look at factors that are similar to what you would do in an event tree. So what's the frequency of leaks? That's based on what piece of equipment. So a piping manifold is going to leak less frequently than a centrifugal compressor, for instance. You'll also look at factors like probability of late ignition, probability of early ignition, occupancy. The base consequence score gets to what the consequence will be. So high pressure gases are going to have lower consequences than liquids that are released below their flash point. Pressure drives risk, and also the flammable factor in terms of confinement is going to help you determine whether your release is going to be a flash fire or an explosion. So this whole process is discussed again in this ISA technical report. And when we put it through its paces, we selected a grade B. So what does that mean? And this is just an example out of the ISA technical report. Every operating company is at liberty to set up their performance criteria. But in terms of the performance criteria that we were using that's compatible with what you see in TR 8407, for a combustible gas hazard that is grade B, we want 80% coverage. We want 99% safety availability, so SIL2 effectively. And this is the mitigation effectiveness. And the proxy for mitigation effectiveness is response time. So we want early detection. We want to be able to detect this in 60 to 90 seconds. Okay, so those are our targets that we picked during our risk analysis. What's the next step? We pick a target.
This table that you're showing right now, is it inside the ISA 84.007?
There is something similar to it in 84007. I think we at Conexus are basically, we are on the committee, but the work product from the committee is usually at least 5 to 10 years old. So we generally are ahead of where the standards committee is. So I don't know if this response time is in ISA 8407. So if you have questions on that or you want more details, feel free to send me emails afterward and I could give you more additional information if you're interested.
Thank you.
Sure, absolutely.
Okay, Ed, there's another question in the chat here
Sure.
about detecting H2 outside. Is there really an effective way to detect it outside since it disperses so quickly?
Yes and no. For the most common detection method for hydrogen is going to be a catalytic bead type detector. There are some infrared point detectors that are used, but generally it's catalytic bead. So for catalytic bead, what's happening is you're passing your gas sample through a hot catalyst pill, and that catalyst should cause the oxidation reaction to occur, further increasing the temperature. So you're basically burning air all the time. And if there's any kind of flammable gas, that's going to result in a temperature increase. The problem is, yes, the wind blows it away. So you need to have a lot of detectors all over the place to be able to detect anything, which is why outdoor gas detection is extremely tough. And again, if there's nothing above it, it's probably not worthwhile to do. Now, that being said, there are other technologies available that cost a lot more money, but are going to work better. So there are tunable diode laser based systems. So you can shoot your, actually, if I go back here and let me try to delete some of this stuff, you can, have a laser emitter and receiver shoot a laser beam across the top of these guys and be able to better, not perfectly, but better detect a leak. Those are a little bit more expensive. The third item is GCI, gas cloud imaging. There are a handful of newer gas detection systems that basically use cameras. And each pixel in the camera, it's not like a traditional camera, it's a LiDAR camera that's using technology to set up a baseline absorption and then compare the current absorption against the baseline. And the camera can actually see, for lack of a better word, gas leaks.
For the GCI, are you referring to the Honeywell Rebellion type camera?
Rebellion Photonics was purchased by Honeywell. Honeywell makes it available. That is probably the archetype. That's the one that's the most common, probably has the biggest user base. But there are other vendors that have not the same technology, but they do a similar thing. Yes, Rebellion Photonics would be an example.
Thank you.
All right, so those are some other options, but again, you need to think about what is the hazard that you're trying to detect. Okay, so now that I've picked my targets, I need to verify the targets. So how do you do that? And in this case study, I am going indoors. What you're looking at here is a 3D model of a facility where they're manufacturing the electrolyzers, and then after they manufacture the electrolyzer, they need to test them to confirm that they're working. So we put together the safeguarding for this facility where the manufacturer of the electrolyzer is testing each unit as it comes off the production line to make sure that it operates. So in this indoor approach, well, regardless if it's indoors or outdoors, the first thing you need to do is run dispersion models. So which pieces of equipment can leak the hydrogen? And then you need to develop design basis scenarios. So we're generally looking at modeling small incipient releases, because if you can detect the small release, you can detect the big release. So we have a representative number of leak points. And for each of those representative number of leak points, we will run a dispersion model. For indoor cases, we will do that dispersion modeling using computational fluid dynamics. For outdoor releases, we might use CFD for hydrogen. We might go with a Gaussian dispersion tool, something like a similarity model like a FAST or a Canary or an effects. But this was indoors, so we did our modeling, and this is just one of the many different leak points that we modeled. So we ran the dispersion model, and you can see an example of what the gas cloud looks like. You see it goes straight to the roof and then kind of starts to pancake out. Now, granted, there are a lot of obstructions on the roof that are going to cause the gas cloud to kind of disperse around. So once you run all of your gas clouds, you then, in whatever tool that you're using, you need to place a bunch of candidate detectors around to determine, for the full slate of dispersion modeling scenarios, which of the release cases were detected, which were not detected, and how long did it take to go into alarm. So here, this is just one release and two detectors, just to show you an example. So I have detector number 1 and detector number 2. Right here is 10% of LFL. So the reason that we model 10% LFL now, I do know, is because this is going to be the set point of the detector. So we do our modeling considering what set point we're going to detect the detector at, because we want to know what's going into detect to alarm and what is not going into alarm. So what we found out here is that for this release, and granted, this is only going to be one of dozens or hundreds of releases that you're going to model, that detector number 1 went into alarm at about, let's call this 25 seconds. And the second detector really probably didn't go into alarm until after about 62 seconds. So what this tells me is that location 1 is a good place for this release. Location 2, not such a good place. It takes too long for the detector to go into alarm. So this type of analysis, this type of graph, you're going to need to do for every scenario that you ran. And the ultimate output of this is you are going to then specify the number of detectors and location of detectors that's going to allow you to achieve your coverage target. In this case, we said 80% within, I think 60 seconds was our time target. Okay. So started out by putting in hundreds of detectors, and then you kind of narrow it down to which ones, what is the minimal and sufficient set of detectors for all of my release scenarios that's going to allow me to achieve my coverage target within the time frame that I've selected.
What was the tool used on the CFD in the last slide?
It was either FDS, Fire Dynamic Simulator from NIST. FDS we generally use for low velocity releases, which makes me believe that FDS is what we used, or it was Open Foam. Open Foam is a lot more difficult to use, but it's a lot more rigorous, and you can more accurately model high velocity releases. So it's going to be one of those two.
Do those allow for detector placement?
No. What you get out of the commercial tools is you're going to get a gigantic pile of data that says what concentration. So what we put into the tool was the detector locations, and you're going to get a gigantic data set that says what was the concentration versus time at that data point. If you want to generate a graph that looks like this, you need to have a bunch of post-processing tools that are going to grab your output and make it easier to use. So yeah, the tools that we're using, they do the calculations well, they generate a bunch of data, but there is a lot of post-processing that you're going to either need to do manually or you're going to need to write some of your own code to do that post-processing.
Okay, thank you.
Okay, so at this point in time, there were 3 parameters, and the first one is coverage check. So we know how many detectors and what location are going to allow us to achieve our coverage. Mitigation effectiveness check, because it's a proxy of time. And then the last item that we have is the safety availability. Now, safety availability, I'm not going to belabor because it's the same SIL verification calculation that you have been doing for decades. You want to learn about it, you can go to the Connexus Learning Management System, you can go take an ISA training class. Ultimately, the probability of failure on demand of the electronics is going to be a function of several parameters. So what is the voting arrangement? And for gas detection systems, that will be either 1 out of n, 1 out of 1, or 2 out of 2 is what we would end up calculating. So am I going to take my executive action when 1 detector sees that the gas cloud exists, or am I going to wait until 2 see the gas cloud before I take my action? And that voting arrangement needs to go into the calculation, but that voting arrangement is also important when you're doing your modeling. Because when you're doing your modeling, right now, we were only looking one detector at a time, which assumes 1 out of 1 voting. If we're not going to shut down until 2 detectors go into alarm, then we're going to need to kind of redo our math so that we're looking at what is the amount of time before 2 detectors simultaneously go into alarm instead of only one going into alarm. So that coverage and your SIL verification calc are intimately tied together. The 2 out of 2 voting not only increases the probability of failure on demand, it also decreases your coverage factor. So in addition to the architecture, failure rates, which are going to come from your equipment vendors or databases, failure modes. So does it fail safe? Does it fail dangerous? What degree of diagnostics do I have on my detection equipment? So the ability of your sensors to self-detect that they're in the failed state. Testing, the more I test something, the shorter the duration that it is in the failed state when it fails. And then I will also need to look potentially at common cause failures. And again, you're going to do this for your entire loop, which is the sensor, the logic solver that you're connected to, and the final element subsystem that is going to bring you to a safe state. So your detectors, your logic solvers, whatever PLC you have it connected to, and then your final element would be de-energization of your electrolyzer. So up on the screen now, you have the premier tool for doing SIL verification calculations, which is Conexus Vertigo. And you'll see that for our case study, we achieve a risk reduction factor of 221. And you can only see the test interval on the transmitter because that's all that we're currently showing on the slide. But you'll see that this was done with a 12-month test interval, which is not really unreasonable for the application that we're looking at. And at this point in time, that is the 3rd performance factor that we needed to confirm. And at that point, we are done. Our design is complete. We know what detectors need to be installed, how many of them, where they need to be located, and we also know how often they need to be tested and all of the other factors that go into the probability of failure on demand calculation. At this point in time, we have a complete, solid design of our gas detection system that is going to meet tolerable risk and conform with all the standards that are out there. So
and I have a question.
Yes.
So for your SIL calc, traditionally in the process industry for gas detections, usually like we don't take any credit unless you need to. And for these specific cases, we are saying there are going to be some kind of executive action. So for gas detection for this application, what would be the final control element? Is that going to be an electrical relay that's stripping off?
Exactly. It is a contactor. So if you look at the electrolyzer, there, part of the electrolyzer is going to be a capacitor, effectively, and that capacitor is going to generate an electrical potential in the water. So this this capacitor is going to receive 3-phase power. Actually, let me draw this a little bit bigger down here. So it's going to receive 3-phase power, and what we use is a contactor, which is basically a glorified, oops, sorry about that, glorified switch. So there's going to be, and again, I am wildly oversimplifying this. If there's any electrical engineers in the crowd, I apologize for the degree to which I'm oversimplifying this. But basically, there's going to be a solenoid or magnetism that is going to cause the contact to close, and that provides electricity to the electrolyzer. When the signal, so you're going to get kind of a signal power to the solenoid, when that gets removed, you lose the magnetism from the solenoid, and then basically there are springs pardon my poor drawing skills, that are going to push those contacts open. So basically, when we de-energize the contactor, it's going to disconnect the three-phase power to the capacitance in the electrolyzer system, which will stop the hydrogen production because you're losing the potential that you're putting across the water. Now, granted, as I discussed earlier, it's not immediate. So as soon as you pull the power off, you don't stop making hydrogen. And that's something that needs to be engineered. It needs to be considered by the team on a case-by-case basis. But ultimately, your final element is going to be that contactor. And if you have trouble finding data for a contactor, the most common application in the process industries would be motor starters. So motor starters that will start and stop a pump or start and stop a compressor work exactly the same way. They're a little bit more sophisticated than just a dumb contactor, but at its heart is the ability to send a signal and either connect or disconnect three-phase power.
Perfect. Thank you.
Mm-hmm. Okay, so in conclusion, and I will definitely turn the floor open to more questions if you have them, so start thinking about them right now. Right now, we are at a potential turning point, and there is a lot of momentum to decarbonization to where even if everyone determined that they didn't want to go that direction, it's going to be kind of hard to turn at this point. And hydrogen is going to be an important part of that decarbonization or green energy for all the reasons that I brought up. Number one, you can generate hydrogen a lot of different ways, starting with fossil fuels, ending with solar or wind power, or maybe if solar and wind power aren't all that they're promised to be, we can always fall back to nuclear energy to generate hydrogen. But hydrogen comes with risk. It is a lot easier to ignite, lower ignition energies. The circumstances under which it can ignite are dramatically increased because the 4% to 75% range between LFL and UFL. As a result, fire and gas detection systems are going to be important safeguards when you're dealing with hydrogen. And that is going to be especially true if you put the equipment indoors. And right now, a lot of the equipment is going indoors because it is sensitive, and the trade-off between the risk of hydrogen versus the environmental degradation of the equipment is kind of pushing you toward putting it inside a closed system like a shipping container. When you are designing your safeguards around electrolyzers, you should be following national and international standards for the design of those safeguards, recognized and generally accepted good engineering practice. And the RAGAGEP, recognized and generally accepted good engineering practice for gas detection and fire detection systems, is going to be ISA TR 8400.07. It is a technical report. I keep getting harassed from a number of different angles to work to get this to become an IEC standard, which I am on the correct IEC committee to start down that road, but one thing at a time. So if you're going to design in accordance with ISA TR 8407, you need to select performance targets and verify that you've achieved those performance targets because it is a performance-based technical report. The performance targets that you're looking at are more than just the SIL. The SIL actually has the smallest contribution. It is the least relevant of all the factors that we're looking at. The most important and the most difficult is going to be the coverage. Determining the coverage means I need to make sure that I have enough detectors, and those detectors are in the correct locations to be able to detect a sufficient fraction of the release scenarios. And I'm going to confirm that by using dispersion modeling and comparing the location of my detectors against the location of my gas clouds. I'm also going to confirm the achievement of response time to make sure that my mitigation effectiveness is sufficient. Just because a detector goes into an alarm 10 minutes later doesn't mean that that's a good location for that detector. And we will calculate the safety availability, especially if we're trying to credit the detector as a safeguard. Now, the secret that I'm going to tell you is that in this case, our coverage, we were able to achieve SIL 1 for this system. And the reason we were able to achieve SIL 1 for this system is that our coverage was dramatically better than 90%. So that 90% that I gave you is a little bit of an example for a general study. You will be able to get risk reduction factors greater than 10 for this type of application, because in a small confined area, you can get really high coverage targets, as opposed to if you tried to get the same coverage target outside, you can completely forget about it. But indoors, it's a possibility. So with that, I'm going to go ahead and leave the slides up while I take some questions, if I haven't already exhausted your ability to ask questions, so that I can kind of go back and forth in different areas. So Chris, do we have any questions sitting out there in the chat?
There's one here. It says, are the gas detectors to be connected directly to PLC, DCS, or through FACP?
Okay, so FACP, I'm going to need some background on that acronym, but while I'm getting the background on that acronym, let me tell you that it depends. The logic solver, the logic system that gas detectors are connected to, varies from industry to industry and application to application. So if you go into, for instance, an oil refinery and you look at the combustible gas detectors, 9 times out of 10, if they have any at all, they're going to be connected into the DCS. And that's generally because the risk is relatively low. In this particular application, we were trying to achieve a SIL target. And because we were trying to achieve a SIL target, we needed it to be outside of the basic process control system. We wanted a risk reduction factor greater than 10. So there we had the gas detectors connected into the safety PLC. Another option that they would use, for instance, in offshore oil and gas applications, would be to use a separate PLC system. So if you look at the standard for offshore oil and gas, there's one logic solver system for basic process control, one logic solver system for ESD, and yet a third logic solver system for fire and gas systems. What I will tell you is the choice is very dependent on industry. And furthermore, it is also dependent on what other RAGA-GEP you're trying to apply. So because we were trying to achieve 61511 compliance for SIL 1, we could not put it in the basic process control system. We would be violating our separation requirements. If, though, we weren't trying to achieve compliance with IEC 61511, now you've got more flexibility to use the DCS, the SIS, or even for the FACP, I think that might have something to do with an automation system that controls the HVAC of the building itself, a facility control system.
Okay, FACP is Fire Alarm Control Panel.
Fire alarm control panel. Okay, that would be kind of more something that you would typically see in an offshore oil and gas platform. Also, if you're looking at just standard building design, there's usually a fire control panel in any large occupied building that's going to be designed in accordance with NFPA 72. But again, this is a gas detection system. NFPA 72, it's got fire alarm code right in the name. So really, a lot of people will want to use the same architecture, the same equipment for gas detection in a building that they use for fire detection in a building, but there's nothing that requires you to do so. There's not a lot of consistency from industry to industry on what happens, which ends up giving you a lot of flexibility, but it also puts the onus on you to know what is customary for the industry that you're in. What else we got?
There was a question out there. Some of the participants answered it, but we'll get your take on it.
Okay.
And which standard separates the controls for system?
Okay, which standard separates controls? That is going to be the IEC 61511 standard. Also, the mothership that sits above 61511 is 61508. Both of those standards set requirements for the separation of basic process control and safety. And the primary intention is that we don't want a single point of failure that will create a hazard and simultaneously prevent you from being able to respond to the hazard. So we don't want a single point of failure that's going to result in a consequence. And the best way to do that is physical and functional separation. So if you want to see the specific details, go into the IEC 61511 standard and look at clause 11.2.10 is where it lays everything out for where you want to do your separation. But again, that's only if you need to comply with this standard. If you don't need to comply with this standard, then you've got more flexibility again. And I've seen gas detectors wired to, you name it. I have seen gas detectors wired to it, from BPCS to SIS to hardwired panel arms. I've seen one of each.
Okay, a couple more here. For electrolyzer inside the building, will it not follow the building code requirements?
Sure, it'll follow the building code requirements, but what building code requirements talk about placement of gas detectors for chemical plants that you put inside a building? Building standards are not written with the idea that we're going to put a chemical plant inside our building. The building standards, look at NFPA 72. What is the thought process that goes into NFPA 72? The thought process that goes into NFPA 72 is I have an occupied building. I have an occupied facility. That facility can suffer a fire. Why is there going to be a fire? The fire is going to occur because of furniture or materials of construction of the building catching on fire. That's why the building codes talk a lot about smoke detectors, because if your carpet or your couch is on fire, it's going to create a dense, smoky flame. Now, if I have an electrolyzer in my building and it catches fire, not only is there not going to be any smoke, you're not even going to be able to see the flame. None of the typical fire detection methods that are in NFPA 72 are going to work for a hydrogen fire. I don't want to make light of the building standards. They are very important. But when you put a chemical plant inside your building, they're not enough. They were never meant to be comprehensive for anything that you could put in that building. They were designed thinking that I'm going to have people, furniture, and normal office type stuff in that building. Now, that being said, they are supplementing so that you can find NFPA standards that talk about storage of lithium ion batteries. NFPA 2 talks about hydrogen applications. So there are some additional standards out of NFPA, but just looking at your normal NFPA 101 for life safety and NFPA 72 for the fire alarm code, those by themselves are not enough. You need to go further than that.
Okay. There's a question here that says,
And are we saying most of the time that the PEM are like applied indoor? Like I know the Cummins example is, are they like all their units are indoor, or are they like like there are some examples for outdoor units? Because I think like what we discussed, that it's very difficult to detect hydrogen outdoor. Like there are ways, but it's very expensive.
Most of the applications that I've seen, the electrolyzer stacks are indoors. And a lot of that is an artifact of how they're manufactured and how they're shipped. So I'm going to go out on a limb and say the preponderance, greater than 50% of the PEM stacks are going to be inside a shipping container. And that's something that you definitely want to work with your equipment vendors to make sure that they've done their due diligence with safeguarding of that entire skid package that they sent you, to make sure that they have the appropriate number and location of gas detectors inside that shipping container that houses the PEM stacks. What else we got, Chris?
What is the inherently safe design for a hydrogen facility? Do we have room for that?
What is the inherently safe design for a hydrogen facility? What is the what is the non-flammable form of hydrogen? Inherently safe is kind of bit of a dream, but there are a lot of design attributes that can make it inherently safer. So when you look at this guy, the primary reason that this happened is because the hydrogen gas cloud got trapped. So in terms of limiting through inherently safer means, you want to design the plant so that it leaks with impunity. What do I mean by that? That means when a leak occurs, it is going to be able to disperse to atmosphere and get to a non-flammable concentration without getting trapped by anything. That'll include ridgeline roofs with roof vents. Also, if you've seen some of the designs, let me try to find a little place to write. So if you've seen some of the hydrogen filling stations, so there's our hydrogen filling station with our little handle for the hydrogen. You'll see that the roofs of these are different from your typical gas station in that they kind of look like this. Boy, I am a horrible artist today. They kind of look like this instead of your typical flat roof that you would see on a gas station. And that's because I leak my hydrogen up. I'm just going to kind of waft it to the side and let it disperse. And I'm not going to develop a really big gas cloud. So making sure that you can't trap any hydrogen that leaks, making sure that the entire area where you could get gas has no mechanism to generate any type of source of ignition. That's going to move you toward inherently safe. But obviously, inherently safe in and of itself, for something that's flammable, is the only way to make it inherently safe would be for hydrogen to not be flammable. But then again, if it's not flammable, it's not worth anything to us. But there are a lot of inherently safer design techniques that will prevent sources of ignition from being present and prevent hydrogen from being able to accumulate into a cloud that can cause harm.
Okay, if
So
we use
in your LOPA, like there was a safeguard, like in HVAC. You didn't take any credit for it. Let's say the safeguard is designed to have sufficient air exchange as per API 500. Would you be able to take credit for it for that specific hydrogen release application?
Absolutely. But for this particular example, if you look at the HVAC system in this building, you'll see HVAC vents where I'm drawing the arrows. All those guys are HVAC vents. And I believe that I can't see any of them, but I believe the HVAC inlets were going to be kind of sitting on the ground level at different spots. So when we did this dispersion model, the gas cloud that you're looking at right there, the HVAC system was running at full capacity, and this is what the gas cloud looked like. So when you're doing this dispersion modeling analysis, you absolutely need to include the HVAC system. Where are the inlets? Where are the outlets? What are the air exchange rates? And sometimes you will come to the conclusion that I cannot develop a gas cloud that will cause harm because my HVAC system is so effective. But for this case study, that was not true.
Okay, a couple more questions. If we use the contactor as a final element, how can we be sure that it will function on demand?
If you disconnect the power, you've now lost the ability to continue to put electricity into the system. You can confirm that a contactor has moved. There are contactors that come with auxiliary switches built into them. So there's, in addition to the three-phase power, there's another contact that when it's closed, it tells you that the contactor is in the closed state. When it's open, it tells you that the contactor is in the open state. You can use that as feedback to go into your safety PLC to let you know whether or not it actually de-energized. And then obviously for any SIS or any safety instrumented function, you need to do periodic proof testing to make sure that the device is going to work when it needs to. And for the calculation, you didn't see it, but in the calculation that I did, there was a 12-month interval for the final element also, that basically every 12 months, we're going to test the device, we're going to de-energize the signal and visually confirm that the contacts open up with the aux contact through physical testing of continuity. So there's the periodic proof test, and then you also, if you want to, can automatically through an auxiliary contact verify that your safety function activated properly. But that verification is not required in accordance with the standard. Only the periodic proof testing is.
Okay. Could explosion relief panels work as a safeguard for container type designs?
Explosion panels would not have worked here. They would have had to have been really, really, really big. So here's my container type design from Cummins. I'm going to have to step back and say, I don't know the consequences of putting in an explosion. So you've got some options. You can put explosion panels. You could make all of the welds on one side sacrificial welds, weak welds, so that if there was an explosion, that whole door would come off. Remember though, you've got three-dimensional confinement inside this. So if you made the entire door sacrificial, how much shock wave am I going to shoot out that door, and what are the consequences of the flying door and this cannon basically in terms of what direction you're going to shoot it? A lot of that is very location specific, and I can't give you a really comprehensive answer other than it's something that you should look at. It's something that you should study. And the other thing I don't know is even if you were able to release the shock wave, what did you do to the equipment that's inside here? So it's probably going to be a good mechanism to reduce the magnitude of the consequences. It's certainly not going to be preventive, but explosion doors, explosion panels, sacrificial welds to allow this thing to collapse elegantly, I'm sure need to be part of the design process. And I'm going to have to beg a little bit of ignorance here because that kind of explosion panel design is not something that I regularly get into. So I will have to defer to someone who knows a little bit more about it than I do.
Okay, thank you. That's all the questions I see in the chat at the moment.
Excellent. Well, if you do end up with any questions as time goes on, I am pretty easy. You could go to the Connexus website and get my profile. It's got my email address, edward.marzell@connexus.com. If you have any questions about this or anything else related to safety, or you want to talk about guitars, whatever you want to talk about, feel free to send me an email. I'm more than happy to talk about pretty much any topic, but I do love talking about chemical process safety.
Thanks everyone for your interest in joining. Someone did mention, is there a possibility of getting these slides?
So the answer is yes. Not only do we have the slides, but there's also a paper. So GCPS requires not just slides, but you also have to write a paper. I think you have to write a paper. I've always written papers. So there are slides and there is a paper. If you would like them, feel free to send us an email. And by us, I mean chris.phillips@connexus.com. We'll be able to send you that information, both the paper and the presentation.
Just Chris with a K. Please note that. Okay, so thanks everyone for joining. I know your time is very important, so we really appreciate you being here. With that, we'll go ahead and close out the webinar. Again, thank you everyone, and I hope you have a good day.
Thanks, everyone.
Thanks, bye.